Alright, so this video is going to be an introduction to linear relationships. What we're going to do is we're going to start with a real world scenario. And from that real world scenario, we're going to look at some data. And from that data, we're going to build what's called a linear model and then use that model to make predictions. Alright, so let's look at our scenario and get started. Our scenario says, Karina is interested in starting a garden and decides to start by planting a tomato plant. The plant starts as a seedling that is only 3 centimeters tall and grows at a constant rate. Each day, Karina goes out to her garden and measures the height of the plant. The table below shows the height of the plant on each day. Alright, so if we're looking at her table, so on day 0, so meaning right when she plants the seedling, so there's no times passed, it's right when she plants it, the seedling is at a height of 3 centimeters. Okay, after 1 day's passed, she goes back outside and measures it, and she finds that the height of the plant is now 5 centimeters. On day 2, she goes out, she measures it, and finds it's at a height of 7 centimeters. And on day 3, she goes out and finds it's at a height of 9 centimeters. Okay, so looking at this data, let's see if we can find a pattern of how the plant grows from day to day. Alright, so if I look, the starting height, no days have passed, 0 days have passed. We start at a height of 3 centimeters. And by the time we get to the 1 day after that, the first day, it's already a height of 5 centimeters. Okay, so it looks like in this first day, it's grown by 2 centimeters. All right, so let's see what the change is from day 1 to day 2. Okay, so on day 1, it's at a height of 5 centimeters. And when she comes back to measure on day 2, it's already a height of 7 centimeters. So it looks like, again, from day 1 to 2, it also grew by 2 centimeters. Okay, if we look from day 2 to day 3, okay, it was at a height of 7. On day 3, it's at a height of 9. And again, it grew 2 centimeters. Okay, so right off the bat, we can see a pretty clear pattern there. It seems that each day we're gaining 2 centimeters on the height of this plant. Okay, so now let's use that pattern. Let's rewrite this table and use this pattern to determine a kind of a rule, or a rule that relates what day it is to the height of the plant on that day. And after we do this, I meant to add this in earlier, it says that Karina wants to be able to predict the height of the plant after 10, 20, and 30 days. We're going to use our linear model. We're going to use this pattern to figure out what the height will be after 10, 20, and 30 days. Okay, so the first thing I'm going to do to figure out what that pattern is I'm going to rewrite my table in a slightly different way. Okay, so let me go ahead and rewrite my table. Okay, so on this side I got days. On this side, I have the height of the plant. Okay. All right, so on day 0, right when she plants it, it's at a height of 3 centimeters. And we said on day 1, okay, it's at a height of 5 centimeters. Well, let's think about, okay, how did we get to this 5 centimeters? Well, what we did was we added 2 centimeters onto our initial height. So I could rewrite this 5 here as 3 plus 2. Now, you might be wondering, why would I do that? Because obviously 3 plus 2 is 5, and that looks simpler than writing that. Well, it's going to turn out that writing it in this way as we move through is going to show us what our underlying pattern is. Okay? So let's look at day 2. Well, at day 2, okay, well, what happened? Well, it's at 7, right? But what happened? Well, what happened was we gained 2 centimeters from the previous day. And we said the previous day it was at a height of 5, or 3 plus 2 centimeters. So if I add 2 centimeters onto that, for the second day, I get it's at a height of 3 centimeters, plus 2 centimeters, plus 2 centimeters. Okay? Let's look at day 3. On day 3, so we were at a height of 9 centimeters, but again, how did we get there? Well, we got there by adding 2 centimeters to what we had before. Okay, and what we had before was 3 plus 2 plus 2. So on this day, we're going to have a height of 3 plus 2 plus 2 plus 2 centimeters. Okay, at this point, we can see that there's actually a pattern between how many 2's we're adding and what day it is. So what do I mean by that? Well, on day 1, I added 1 2. And on day 2, I added 2 2's. And on day 3, I added 3 2's. Okay, so it looks like whatever day it is, that tells me the number of 2's I need to add. And that's going to be the rule that we use to create what's called our linear model. And I'll explain that more once we get there. Okay. Before we get to that point, let's use something we know about from the past about repeated addition. So a long time ago, you learned about repeated addition. You learned that repeated addition could be more succinctly described as multiplication. It can be written in a shorter way as multiplication. So what do I mean by that? Well, here on the first day, I could write this as 3 plus 2, but I could also write it, if I chose, as 3 plus 2 times 1, because I'm adding one set of 2, right? So you need to think of multiplication as being sets of. So, generally you read it, left to right, 2 sets of 1, but for our purposes, we're going to think about this as, okay, on the first day, I start with 3. On the first day, I add one set of 2. Okay, on the second day, I added 2 sets of 2. 2 sets of 2. Okay. Well, on the third day, I added 3 sets of 2. So I had 3 2's adding here, so I had 3 sets of 2. And I could continue this pattern because I know each day I'm just going to add on another 2. So let's go and do that for the fourth day. And also in the problem, a minor detail, it said that this plant was growing at a constant rate. And what that means is it's gaining the same amount each day. So that's how I know it's not going to go up by 5 this time, or up just by 1 maybe, right? It's going to go up by the same amount each day. Okay, so on the fourth day, okay, well, I'm going to have 3 plus 2 plus 2 plus 2 plus 2, right? Because again, I'm just adding one more 2 on the end there. Okay? Well, on the fourth day, I added 4 2's. So that'd be equal to 3 plus 4 sets of 2. 4 sets of 2. Okay, at this point, we can generalize a pattern. Okay? I can see on day 1, I add 1 2. Or another way to think about it, I multiply by 1. On day 2, I multiply by 2. On day 3, I multiply by 3. On day 4, I multiply by 4. So it looks like my general pattern is I'm taking the starting height of the plant, 3, plus 2 times the number of days it's been. Okay, so that's my general pattern there. Whatever day it is, that's how many 2's I add, or thinking about it in terms of multiplication, that's what I multiply by. Okay, this right here is what we call a mathematical expression. Okay, I'm going to take it a step further, and from this mathematical expression, I'm going to write what's called a mathematical equation. Okay? All right, so what do I mean by that? Well, what was this column here even showing us? What was this column? What is this calculation telling us each time we do it? Well, what's telling us is the height of the plant on any day. So, we could write that the height of the plant is equal to 3 plus 2 times whatever day it is. And this is what we call a linear equation. And I should have said it before, this is a mathematical expression. This is also called a linear expression. I'm going to explain why it's linear here in just a moment. This is what we call a linear expression. And this is a linear equation. Now, in math, we like to be lazy. We don't like to write out phrases like this or words like this in our equations. So what I'm going to do is I'm going to pick a letter to represent this part, this height of plant, and I'm going to pick a letter to represent day. Okay, well, let's think, what would be a smart choice of a letter to represent, which is also a variable we're going to talk about. What would be a good letter or variable to use for height of plant? Okay, well, you could use H for height or maybe P for plant. It doesn't actually matter. I'm going to use H this time for height. Okay, so I'm going to replace this with an H. So I have H is equal to 3 plus 2 times, okay. Well, now let's think, what would be a good letter to use for day? Okay, well, a lot of times you use kind of like the first letter of the word or the first letter of the phrase. I'm going to use D for days. So now we have a linear equation that says H is equal to 3 plus 2 times D. Okay, now this has two names. This is called a linear equation. And often when we apply a linear equation, when we're using a linear equation in a real life scenario like growing a tomato plant, we can also refer to it as a linear model. Oops, sorry. Smartboard has issues sometimes. It switches color by itself. Give me just a second. This is a linear model. Oops. Okay. All right. Now that we have a linear model, we can actually use this model to answer that question, those questions that Karina was asking before. We can use this model to predict the height of the plant after 10, 20, and 30 days. Okay, so let's do that. Well, when we looked at our table up here, well, we said, okay, how do we find the height? Well, whatever day it is, that's what we multiply the 2 by here. That's what this linear equation or this linear model says. Say, whatever day it is, take 3 plus 2 times those number of days. Okay, so let's use this model and make a prediction of the height after 10 days. Okay, so our height H is going to be equal to 3 plus 2 times 10 days. Okay, and then now we're just going to use our order of operations. We're going to simplify this. Okay, well 2 times 10 is 20. So H is equal to 3 plus 20. 3 plus 20 is 23. And so after 10 days, our model predicts that the plant will be at a height of 23 centimeters. Okay. All right, now let's use our model to predict what the height will be after 20 days. Okay, so after 20 days, the height is going to be 3 plus 2 times 20 days. Again, use our order of operations. You've got to multiply before we add. Okay, so 2 times 20 is 40. So H is equal to 3 plus 40. 3 plus 40, of course, is 43. And so after 20 days, our model predicts that our plant will be a height of 43 centimeters. All right, let's predict the height after 30 days. Okay, so after 30 days, our height will be equal to 3 plus 2 times 30 days. Oops. Okay, again, use our order of operations. 2 times 30 is 60. And 3 plus 60, of course, is 63. Okay, so let's recap and look at what we've done so far. Let's go back up to the top. Okay. All right, so we started with a real life scenario. Okay. From that real life scenario, we looked at a table, or we made a table, Karina made a table, of data of how it changed, through the days and how the height of the plant changed. So we started with a scenario, and then we looked at a table. And then from that table, we generalized a pattern. And from that pattern, we wrote an expression, a linear expression. And from that linear expression, we wrote a linear equation. And then from there, of course, we replaced these phrases, this word here, with letters, because we like to be lazy. Okay. So now we have our linear equation or our linear model, right? It's modeling the height of how the height of the plant changes over time. Okay? And from that model, we made predictions of the height at 10, at 20, and at 30 days. Okay? Now, why do we call this a linear
High
model?
school teacher's lunch is being served outside if you're interested.
Sorry about that. I can edit that out. Okay, so why do we call this a linear model? Okay, well, the reason let's look at a graph and see why we would call this a linear model. Okay, so I have a graph here, and on this graph, I have my days going across what's called the horizontal axis, right? Okay, so here's day 0, day 1, day 2, day 3, so on and so forth. Okay, on my vertical axis, I have the height of the plant. So here I have a height of 1 centimeters, 2 centimeters, 3 centimeters, so on and so forth. Okay, so what I'm going to do is I'm going to graph the data that Karina took. Okay, so if we look back at the table, we would see that, okay, on day 0, right when she plants the plant, okay, on day 0, it was at a height of 3 centimeters. So again, at day 0, I'm going to go over to day 0, I'm going to go up to a height of 3 centimeters, and I'm going to put a point. Okay. All right. At day 1, she measured the plant to have a height of 5 centimeters. So at day 1, I'm going to go over to day 1, I'm going to go up to a height of 5 centimeters, and I'm going to put a point. Okay, on day 2, she measured a height of 7 centimeters. So at day 2, I'm going to put a point up here at 7 centimeters. And finally, at day 3, she measured a height. So over at day 3, she went out and measured a height up at 9 centimeters. So I'm going to put over at 3, I'm going to put a point up here at 9 centimeters. Now, looking at this graph, we can now see why you would call this a linear model or a linear equation. It's because the data that we drew this model from, I'm going to get to the connection between the model and the data here in just a moment, but all of our data points are in line with each other. They all follow kind of a straight line pattern here, right? And so that's why we call this a linear model, or this would be called linear data. It's all linear. Linear data, a linear expression, a linear equation, linear model, whatever, right? It's all linear. It's all because it falls in line with each other. They're all in line with each other, right? Okay, but now let's think about this. These are just the data points that Karina measured, right? Well, if we think about it, the plant's growing continuously. It's growing throughout the day. It doesn't just magically jump from 3 centimeters to 5 centimeters. So if we had gone outside and maybe measured it, so somewhere between day 0 and day 1, maybe after a half day, well, after a half day, we have gone up here and measured some point around in here. Okay, something that falls in line with everything. Or maybe if I went to, day 1.5, I would come up here and measure something that's kind of that's still in line with everything right here. And actually, at any point, if I went out there and measured it every second, or every millisecond, or every nanosecond, I would get, I could go over every 1 second, I would get some little point that was still in line with all of this. And so if I think about it, if I measured all those little seconds in every single day, I would have a bunch of little dots all right beside each other, all about touching each other, right, going up this line. And they would all be in line with each other, all forming this linear shape, right? And so that's kind of the connection between our linear model and this linear data, is that I can think about coming in here after 1 nanosecond or 1 millisecond or whatever, some really small unit of time, and going up and filling in a little dot here, and then a little dot here, and a little dot here, and a little dot here. And because we can't draw all the little dots, because that'd be impossible to do as people, what we do is we connect all these dots with a solid line. Right? So we connect all these with a perfectly straight, solid line, which I'm going to do by hand now, so it's not going to be perfectly straight, but just to get the idea, be something kind of like that, right? Something kind of like that to kind of represent all these little dots being filled in. Right? And so this is what we call a graph of a linear equation. Now, in the next video, what we're going to do is we're going to look at our linear equation, our linear model, and we're going to look at our graph, and we're going to draw some connections between the two.